dispersion, scattering, interference, and diffraction. How do these wave-like behaviors of light differ from one another? Hello, Sci-Pals! I am Ma'am Angelica Sagosio, your science teacher for today. In this episode of Agham Alam Hub, we are going to discuss the difference among the four wave-like behaviors of light. We will demonstrate how waves of light undergo dispersion, scattering, interference, and diffraction. Finally, we will appreciate the different real-life applications of the wave-like behaviors of light. In the next few minutes, we will explore science for another moment. Light is intimately involved with our daily lives. Many unique properties of light are extremely fascinating. Light waves across the electromagnetic spectrum behave in similar ways. When a light wave encounters an object, they are either transmitted, reflected, absorbed, refracted, polarized, diffracted, or scattered depending on the composition of the object and the wavelength of the light. The word wavelength is used to express the wave or undulating property of light. It is the distance that light travels in one oscillation and is often expressed using a unit called nanometer. 1 nanometer is equal to 1 billionth of a meter. Among the different waves in the electromagnetic spectrum, our eyes can only see light that has a wavelength between approximately 400 to 700 nanometers. This range is called the visible light. Let us now discuss the four wave-like behaviors of light. White light, such as the light from the sun, is actually a mixture of different colored lights, which possess different wavelengths. Using a prism, let us separate the colors of white light. When light is refracted, which means it traveled from one medium to another, the different wavelengths of light are bent at slightly different angles. This phenomenon is called dispersion of light. Light that strikes a prism refracts and moves to its interior. It then reflects within the prism and refracts once more when exiting the material. Due to the difference of wavelengths of the colors of light, the beam that exits the material displays the colors of the rainbow. The same phenomenon happens in the atmosphere. When there is enough water droplets in the air, they act just like a prism, causing dispersion that leads to the formation of a rainbow. Scattering of light is the phenomenon that occurs when light is absorbed and irradiated by particles in the air, which are about the size of gas molecules. To visualize how scattering of light occurs, let us demonstrate it in this simple experiment. In a beaker, let us thoroughly mix 5 grams of starch to 500 milliliters of water. Meanwhile, in a separate beaker, Let us thoroughly mix 5 grams of sugar to 500 milliliters of water. Now, let us focus a beam of laser light towards the beakers. What do you observe? That's right! In the sugar solution, the laser light simply passed through the beaker. However, in the starch and water mixture, the laser light is scattered through the beaker, resulting to a glowing appearance. This phenomenon is known as Tyndall effect. Tyndall effect is the scattering of beam of light by a medium containing small suspended particles like smoke or dust in a room, which makes light beam entering a window visible. The same phenomenon explains why the sky appears blue during the day and orange or red during sunrise and sunset. This is more commonly known to physicists as Rayleigh scattering. Light from the sun reaches the Earth after traveling through space. It scatters when striking the various particles and molecules in the atmosphere. A part of this light returns to the outer space, while the remaining light reaches the surface of the Earth after traveling through the atmosphere. The level of scattering of light depends on its wavelength, and of the lights that our eyes can see, blue light is more intensely scattered. This is why the sky appears blue to our eyes during the day. However, during sunrise and sunset, the sky can appear orange or red to our eyes. This is because when the position of the sun is lower, the distance that the light travels through the atmosphere becomes longer, and the blue light is gradually scattered and weakens. Therefore, the remaining red or orange light reaches our eyes. The phenomenon that occurs when the light waves collide with each other is called interference. Light moves in various directions, so the light waves are constantly striking against each other. When the peaks or crests of these waves overlap, they become even larger. This is called constructive interference. Meanwhile, when the crests and valleys or troughs of the waves collide, the waves cancel each other out. This is called destructive interference. Through this simple experiment, let us observe how interference occurs. Notice that when the two beams of light meet, there are areas which appear brighter while others are darker. The parts that show brighter light indicates the existence of constructive interference, while on the other hand, the darker part indicates destructive interference. The same phenomenon explains why we see various colors in soap bubbles. A soap bubble is made of an extremely thin film. Light reflecting from the outer and inner sides of this film interferes with each other to cause the colors that we see. Moreover, the viewing angle of the light interference occurring at the soap bubble film changes due to ceaseless movement of the soap bubble. Due to the waves of light repeatedly intensifying and canceling each other out, our eyes see mysterious and constantly changing colors. Another wave-like behavior of light is diffraction. Diffraction is the bending of light around corners of obstacles or barriers. It occurs when light waves pass through these obstacles or barriers or through small openings. There are different degrees of bending or diffraction. This property of light is not easy to observe because the bending is very small. Let us demonstrate diffraction of light by changing the size of the opening of a slit between two cardboards. The degree of diffraction depends on the wavelength of the wave and the size of the opening of the object. In general, the longer the wavelength compared to the width of the opening or object, the greater the diffraction. Hologram formation is possible through diffraction. A hologram is a recording of an optical interference pattern which can produce a 3D light field using diffraction. Light passing through the hologram is refracted in various directions, producing both real and virtual images of the object used to expose the film. The interference pattern is similar to the pattern produced by the object. Thus, the image looks like the object and appear three-dimensional. Understanding the difference among the wave-like behaviors of light is a significant part of physics. To be able to describe light phenomena is of great importance because most of the information we receive from our physical environment involves light and sight. In this episode of Agham Alam Hub, we discussed the difference among the four wave-like behaviors of light and demonstrated how they occur. We also provided different real-life applications of dispersion, scattering, interference, and diffraction. Dispersion of light happens when light is refracted and the different wavelengths of light are bent at slightly different angles. Due to the difference of wavelengths of the colors of light, the beam that exits the material displays the colors of the rainbow. Scattering of light is the phenomenon that occurs when light is absorbed and irradiated by the particles in the air, which are about the size of gas molecules. This phenomenon explains why the sky is blue during the day and why the sky is orange or red during sunrise and sunset. Interference occurs when light moves in various directions, so the light waves are constantly striking against each other. Constructive interference happens when the crests of these waves overlap and become even larger. Destructive interference occurs when the crests and troughs of the waves collide, canceling each other out. The appearance of the different colors in a soap bubble is explained by this phenomenon. Diffraction is the bending of light around corners of obstacles or barriers. It occurs when light waves pass through these obstacles or barriers or through small openings. Hologram formation is an application of this phenomenon. Understanding the difference among the wave-like behaviors of light is a significant part of physics. To be able to describe light phenomena is of great importance because most of the information we receive from our physical environment involves light and sight. That's all for today, Sci-Pals! Don't forget to like, share, subscribe, and turn on the notification bell. See you again next week for another moment. Only here in Agham Alam Hub, Palacha, SciTech Portal. Bye!